I'm recording this class, and I'm going to share this online. Please let me know if you have any problem with recording. Otherwise, I'm assuming that everyone is fine with recording and sharing this class online. It might be on Blackboard or somewhere else. Please let me know if you have any problem. Otherwise, it means that you're okay with that. In continuation of what we did on artificial intelligence, the basic concepts, the introduction, the background, where did it come from, what was the general idea, and what does it mean, the requirements in math, requirements in other disciplines, generally about AI itself. Now we need some sort of introduction to AI and main components of AI. Again, this would be sort of high-level discussion. We are not getting into many details. We are getting closer to the core of the idea. Before going to algorithm, before going to what we need to do, I want to introduce other concepts which are very, very important to understand the artificial intelligence itself, and the algorithm that we are going to discuss in next few chapters. What I'm going to do will be, I'm going to introduce agent and environment concept. When I want to apply, when I want to use AI, I need to have this concept of agent and environment definition and make it clear what does it mean and what are the requirements and interaction between these two. Also, we need to define good behavior. What does it mean, then rationality, and how do you implement rationality of your agent in interaction with environment. Then talking about nature of the environments or characteristics of the environment, and also the structure or characteristics or parameters of the agent. Well, these are required to have an understanding of where your AI goes, how your AI works, and how it interacts with the environment. We need to understand that before doing anything else. In chapter 1, in previous chapter, we talked about the being rational agent. We talk about details and what does it mean, what are the consequences of accepting something is rational. We decided, rather than while focusing on other concepts, rather than just being like human, or based on what's going on inside the mind of the agent, we more focus on what's happening outside, how this agent interacts with environment. And according to that, we defined rational. Rational means when your agent perceives from outside and behaves in a way that you can accept that as a rational behavior. Well, now I'm going to talk about this topic in more details, in deeper. And our plan is to use this concept to develop a small set of design principles for building successful agents, system that can reasonably be called intelligent. An agent is anything that can be viewed as perceiving its environment through sensors and acting upon environment through actuators. So basic concepts is, and keywords are clear here. When I'm talking about agent, means that I'm assuming that I have a creature, I have a concept, I have a system which can perceive from environment. It goes through sensors, definitely, and can affect the environment, can reply to inputs, will be affected and can affect also the environment as well through sensors and actuators. For instance, if we consider human as an agent, which has a similar definition, similar behavior, ears, eyes, other sensory inputs are your input sensors. And actuators like hand, legs, mouth, other part of human body are actuators. Very basic. So this idea of agent actually is coming from living creatures. In robotic agent, on the other hand, you can consider things like camera, like infrared range finder, other type of sensors you have for different kind of measurements and environment interaction inputs, and actuators, things like motors, hydraulic, pneumatic. There are actuators or outputs of that agent. We use the term percept to refer to agent's perceptual input at any given instant. An agent percept sequence is a complete history of everything the agent has ever perceived. See, here I'm introducing another concept, sequence of percept. So in most of the cases, we might be able to make decision based on instant input. So at the moment I have an input and I can make decision what to do based on that input. But in many other cases, we have to make decision based on sequence of percepts. I received this and this and this and this, and then I need to decide. And even in what order I received them might make a difference in my decision. In general, an agent's choice of action at any given instant can depend on the entire percept sequence observed to date, but not on anything it hasn't perceived. That's the basic, if you remember in our definition in first chapter, well, knowledge is based on what we perceive. So our agent normally, based on those inputs it receives, can make decision. By specifying the agent's choice of action for every possible percept sequence, we have said more or less everything there is to say about the agent. Mathematically speaking, we say that an agent's behavior is described by the agent function that maps any given percept sequence to an action. Okay, so mathematically, we can define an agent function as something like this: a function which maps percepts to actions. Okay, a function which receives inputs and based on inputs makes a decision about next action. The agent program or algorithm runs on physical architecture and produces F. So to make this, we have to have an algorithm, and this algorithm is implemented in a program language. It can be Python, C, MATLAB, or anything else, right? Not necessarily an ordinary computer program. And this program is on a physical structure of the agent. Physical structure runs the system and also applies the decisions to the environment. So one agent, therefore, will be a physical structure plus its program. It disconnected me again. Sorry, it disconnected me. I have to reconnect the slide. It might happen, I don't know, today been too much. Okay, so everyone can see the slide. Can yes. Everyone see the slide? Yeah, good. All right. So conceptually, when we talk about an agent and environment, actually there are like two concepts interacting with each other. So agent has actuators, perceives information from environment, and acts into the environment. Or in a block diagram based, we use this. We're gonna use this block diagram more. I have a concept like environment and agent. These two are interacting with each other through perception, what agent understands from environment, and actions as agent applies to the environment. Okay? So please have a look at this. And do you think we need to add anything here? Is it complete? Yes, no. You at least have to have a choice, right? So I'm assuming you're an agent on the other side, and class is environment. You perceive and you respond. Yes, no, nothing. Memory. Let me stop my video broadcast. Missing memory. Yeah, memory is one of the. Well, we don't see it. It might be there. It might be there, but it's not in a written form. Anything else? Or you can say, yeah, it's complete. Just say yes or no. Okay, good. All right. So we can imagine tabulating the agent function that describes any given agent for most, any given agent for most agents, okay? This would be a very large table. So what does it mean tabulating? Well, interaction between your agent and environment are based on what your agent receives or understands or perceives from environment, and based on that, make an action. One way, probably the simplest way of doing it is if I create a table, an instruction table, say if this happened, if P0 happen, whatever it is, make action 0. If P1 happen, do action A1. If P2 happen, A2, and so on, so forth, till if well, you perceive situation N, do action N. Creating a table, a lookup table for actions of your agent. Given an agent experiment with, we can in principle construct this table by trying out all possible percept sequences and recording which action the agent does in response. The table is, of course, an external characterization of the agent. So what do you think? Is it a good idea to having tabulating? Internally, the agent function for an artificial agent will be implemented by an agent program. It is important to keep these two ideas distinct: agent function and agent program. Agent function is an abstract mathematical description. How your agent works mathematically. This might be more conceptual rather than just a written program. It's more general, it's higher level, right? And agent program is a concrete implementation running within the physical system. So you have some concept, we talk about that. We talk about this more in this class. Implementation is it can be a program language in any language you know. Okay, to illustrate, to show this idea, we use a very simple example: the vacuum cleaner wall shown in figure 2.2. this one. Okay, so I'm getting into it, right? I'm starting learning more about agents. Now let's define our first simple agent. An agent which is responsible to clean up its environment, its world has only two squares. This agent can be either in square A or square B. Each square might have two conditions, one of two conditions. Either it's dirty or clean. Okay, so a very super simple structure. I have a word of two locations, two squares. I have an agent which can move from A to B or from B to A. So this agent can go either left or right. And it also can suck, means clean, suck up the dirt, clean the environment, or do nothing, no operation. So this is a kind of definition of our agent, right? Here I have an agent. The percepts this agent can get is the location and state of the environment. My agent can understand in which square it is right now, or what is the situation of that square. It has sensors, let's say, can detect if it's dirty or not, it's clean or not, and also can move left and right. So let's consider this simple agent. All right. It's also a made-up one. So we can invent many variations. You can extend this to many other forms. This particular word has just two locations, square A, square B. Vacuum or agent perceives which square it is in and whether there is dirt in that square or not. It can choose. So here we are assuming that agent can perceive the square which is in it right now. So if it's in square A, it can check A, not B. Unless it moves to B, then it can check B as well. You could say that your agent also can detect what is the situation at B when it's in A. No, not that. We are limiting ourselves. This one can be either in A or in B. It can check A when it's in A. It can check B when it's in B. It can choose to move left or right, or it can suck up the dirt or do nothing. One very simple agent function is the following. So look at this. This is the concept of work we expect from this agent. If the current square is dirty, then suck. Otherwise, move to the other square. This is not a program, okay? This is the concept. This is the model you want your program to run. This is the algorithm. A partial tabulation of this agent function is shown in figure 2.3. This one. Look, this is an example of possibilities. So we are in A, and A is clean. Move right. That would be the action. We can define this. We can write this down and embed this inside our agent, inside our vacuum cleaner. You are well, if you are in A and it's dirty, then suck up. If you are in B and it's clean, move left. If you are in B and dirty, suck up. If you are in A, it's clean, and you are in A, it's clean, go to right. If you are in A was clean, and you are in A, and A is dirty now, just suck up. And you can add that and make it more and more complicated. You can create a table to consider all possible situations. all possible possible decisions which your agent need to make at different for different cases. I need to go back to get back to my, all right, okay. So looking at figure 2.3, we see that various vacuum word agent can be defined simply by filling in the right-hand column in the various ways. So when you're creating that table of perceived actions, you can do whatever you want. You can define it. That's where you define behavior of your agent. That's where you make your agent look like rational or irrational. The obvious question then is, what is the right way to fill out the table? That's how we program, right? What makes an agent good or bad, intelligent or stupid? A rational agent is one that does the right thing. Conceptually speaking, every entry in the table for the agent function is filled out correctly. Obviously, doing the right thing is better than doing the wrong thing. That's obvious. But what does it mean to do the right thing? The concept of being right and wrong might be rather complicated. Okay. So we need to define and make it clear what is a good behavior, what would be good and what would be bad. The concept of rationality, right? We answered this age-old question in an age-old way by considering the consequences of agent behavior. See, another keyword, sorry. Consequences, all right? So your agent perceives, your agent decides what action to do. Now we are talking about the third item, which is the consequences of the action. Consequences of the action. When an agent is plunked down in an environment, it generates a sequence of actions according to the perception from environment. According to the percepts it receives. Okay, this sequence of actions causes environment to go through a sequence of states. Another keyword. We're introducing ourselves to the concept of artificial intelligence. That's why I'm just focusing on basic concepts here. So again, perception, take action. When it takes action by time, it creates sequence of actions. To make judgment about how good or bad is your agent. This sequence of actions or each step of action will affect environment. For example, in our agent, in our vacuum cleaner agent, you have a dirty environment. And this environment might become again dirty and dirty and dirty, and your vacuum cleaner has to move around and make it clean. It might become dirty in a specific pattern. So like you always have more dirt in square A rather than square B. Or the chance of getting dirty in square A is higher. The probability is much higher than B. Or, you know, all different combinations you can imagine. We say our agent is rational, behaves well when consequences of its movement look better in environment. If the sequence is desirable, if what we like, if what we prefer to see, then agent has performed well. So being desirable and what we want, and in this case, in this example, you can say, all right, I want my environment to be clean. So if this agent can keep it clean, I would say it's a good behavior. Well, it can go down deeper. You know, we're entering the rabbit hole. The rabbit. You know what is the rabbit hole, right? We are entering this down deep concepts of artificial intelligence. So I'm just taking you there. This notion of desirability is captured by the performance of measure. Now, we have to speak numbers. You're saying it's desirable. How desirable it is? How do you define that? How do you evaluate that? How do you measure this performance? Okay, that evaluates any given sequence of environment states. Sequence of environment states. We can evaluate, but you should be able to define being well or performing well in terms of sequence of environment states. Any questions so far? Okay, so everyone is following me. Okay, I wish, well, I don't know. I'll try to explain, but please, if it's confusing, let me know. Okay. Okay. We have found a very good solution. I'm very happy with what I have. Now, AI problem is as simple as this. Define your environment, define your agent, okay, and then start filling up a table of possible perceptions and required movements. You have the table, you're done. You have an intelligent, you have a rational agent. Does it sound okay to you? For example, consider our vacuum cleaner. We might propose to measure performance by the amount of dirt cleaned up in the single 8-hour shift. Okay, so I'm happy with what I have. I want to measure now. So let's say I have programmed same agent with my program, and someone else in class, let's say the last person who have common genome, also has programmed his own agent, and we both have similar, physically similar agents. We want to see whose program is better, who has a higher performance. Okay, we ask in the class, how do you define performance? In general, class says, all right, so performance means we'll look into the environment over 8 hours. Whoever can keep the environment clean, whoever can collect more dirt, the amount of dirt cleaned off in a single 8 hour is a good measure. What do you think? Is it a good measure? Answers yes or no. As simple as that. Y or N. The simplest key you can enter. Gino says no. He says no because he was my competitor. He's against me. All right. Only if there is same amount of dirt for both tests. Yeah, same amount of dirt. Yeah, exactly. Maria says no. Alex says no. Jason says no. Nikita says yeah. Nikita says, assuming that we have same amount of dirt, we are talking about same amount of dirt in two environments. Yes, exact environments, exact amount of the dirt. It's not a good. It's not a good solution. So, how much dirt it collects, or how much dirt it cleans? It's not a good option. Why? Can someone give me a reason? Why don't you think it's a good idea to measure performance of our agent, rationality of our agent by using how much dirt it cleans? Why not? Which machine moved more? Okay, you're considering something else, right? Okay. So you think it's not a good decision because you have to include others. How much area was covered? Assuming same area for both agents. This is one of your actions. Okay, so all right, very good, very good. We have ideas. We have ideas, right? We have ideas. But look at this scenario. With a rational agent, of course, what you ask for is what you get, right? A rational agent can maximize this performance, as I defined above, measured by cleaning up the dirt, then dumping it all back to the floor, and then clean it up again. And over. An evil solution, right? Like some people do, right? Well, you ask to do something, if you measure, if you pay based on how it sucked up, how much dirt it sucked up, it will do that, right? And smart, intelligent agent will do that. Dumps it back, sucks it up. Dumps it back, sucks it up. Because you pay, you measure the performance in your program based on how much it sucks up. So it's not a good performance. It means that while it might cover part of it, but it's not a good performance measure because we are assuming that this agent has other qualities as well. We didn't expect that to do such a thing. In terms of this single performance measure, it's good. It's a good solution, but it's not what we expect. A more suitable performance measure would be a reward. This is also a keyword, reward. The agent for having a clean floor. So instead of how much dirt it sucks up, we paid reward, okay? We actually give positives to our agent for the number of clean squares per hour, or clean squares, clean area over 8 hours. Okay. For example, the one, 1 point could be awarded for each clean square of each time step. So over 8 hours, we divide our 8 hours. Let's say minimum takes 2 minutes, 5 minutes. I don't know how many minutes, X minutes to clean and square. We divide our time to those minimum time steps. Then we measure how many time steps floor being clean, have been kept clean, okay? And we, sorry, and we reward, and we, sorry, I apologize. And we award our agent for that time, for that time. And also, we can define penalty. Penalty for how much electricity is consuming, how much noise it's creating, or as we had in suggestions, how much it has moved, right? So you're making it more complicated now. We defined reward, we defined penalty. As a general rule, it is better to design performance measurements according to what one actually wants in the environment, rather than according to how one thinks the agent should behave. So for performance, as a general rule, it's better to focus on environment. Instead of saying, we're gonna award agent based on how much dirt it sucks up, this is based on agent. We would say how much environment is clean. See the size. This is kind of general rule when I'm writing AI later for different behaviors. Any question or any suggestion so far? Okay, very good. I'm coming back in videos. Hopefully, it'll be okay. So, what do you think? Is it a rational agent? talk about rationality. Consider the simple vacuum cleaner agent that cleans a square if it is dirty and moves to the other square if not. Our vacuum cleaner agent. This is the agent function tabulated in figure 2.3 that we had before. Is this a rational agent? Sorry. Is this a rational agent? Answer means depends, right? First, we need to say what is the performance measure and what is known about the environment and what sensors and what actuators and how agent behaves in that, and with evaluation of all of those, we can talk about rationality of this agent, not just based on what we think we have programmed. Let us assume the following of the cleaner to have a rational agent. The performance measure of var 1 point for each clean square at each time step. So we are going to give 1 point of award for each square per time step over a lifetime of 1,000 time steps. So the best case is all squares are clean for all the time, means that for 2 squares 1,000 times you get maximum 2,000 awards, max, if you have n squares. The geography of the environment is known as a period. We already know that. See, here's another point. Our agent already knows how environment looks like. It has 2 squares. It moves from left to right, right to left, to go through one state to one square to the other one. But the dirt distribution and the initial location of the agent are not. See, another point. How much information our agent knows about the environment, how much information it doesn't. So for example, we didn't say we're assuming that agent initially is at square A or B, or what is the cleanness or being dirty in the squares. Clean squares stay clean, and sucking cleans the current, sucking cleans the current square. So defining the function. How to clean and how to stay clean. The left and right action move the agent left and right, except when this would take the agent outside of the environment. There is a wall around our environment, in which case the agent remains where it is. So if you're at A and you try to move left, you will stay at A. So you're at A, action is move left, result will be A. The only available action are left, right, and suck. So we have 3, and the agent correctly perceives location and whether location it contains dirt or not. One can see easily that the same agent would be irrational under different circumstances. So giving you an example. Once all the dirt is cleaned up, the agent will oscillate needlessly back and forth if the performance measure includes a penalty of 1 point for each movement left or right. The agent will behave poorly, right? So that makes sense, right? I have programmed my agent. If this is my agent, I'm going to award you for each square clean over time step, and I'm going to punish you, give you penalty for each square being dirty over time. So if I'm going to punish these for being dirty in each square, in dirt in each square, it starts going from here to here continuously, regardless to whether it's clean or not. It just continuously moves around. A better agent for this case would do nothing once it is sure that all the squares are clean. if clean squares can become dirty, again, the agent should occasionally check and re-clean them if needed. If the geography of the environment is unknown, so another dimension, if the geography of the environment is unknown, the agent will need to explore rather than just stick to square A and B. This is another concept. So if I change my environment from 2 to something, different, moving around. So in that case, if you have more squares and your agent doesn't know how many squares it has, and even in a different shape, not just in a bigger square shape, it can be any other shape, then in addition to just going left and right, up and down, your agent has to have a plan how to explore the environment. Rational agent, for each possible percept sequence, for each possible percept sequence, a rational agent should select an action that is expected to maximize its performance. So maximizing performance. This is another concept. Maximizing the performance. All right. Based on the evidence provided by the percept sequence and whatever built-in knowledge the agent has. So rational agent is the one, it's a better definition now. It's the one that tries, based on perception sequences, takes actions to make the performance better, to maximize the performance. So percept, action, and performance. Well, concept of expected will be explained later. What do you mean by expected? But here, just consider perception, action, and performance. Performance measure, an objective criterion for success of an agent. So performance itself on its own is not success. Success is defined as how much performance is good. How much performance do you want to receive? Do you want to have using this agent? For example, performance measure of the vacuum cleaner, as I said, could be a combination of amount of dirt cleaned up, amount of time taken, amount of electricity consumed, amount of noise generated, and so on and so forth. So you can define performance as a combination of different parameters in your agent. We need to be careful to distinguish between rationality and omniscience. An omniscient agent knows the actual outcome of its action and can act accordingly. Omniscient is impossible in reality. Kind of with God type power, okay? It has a vision, top vision of everything, understand everything. No, our agent is in the environment. It's understanding based on perception from environment, okay? Perception of the environment. For example, I'm walking along the Champs-Élysées one day and I see an old friend across the street. Okay, there is no traffic nearby and I'm not otherwise engaged. So being rational, I started to cross the street. Meanwhile, a 33,000 feet cargo flight door falls off a passing, or falls off from a passing airliner. And before I make it through the other side of the street, I'm flattened on the street. Well, sounds like a joke, but well, based on possibility, based on just pure calculation, it might happen, right? So in Paris, in Champs-Élysées, you see an old friend, you want to cross the street, you check there is no traffic, there is nothing else to make you worry. You start walking, but suddenly something out of nowhere comes and hits you. So would you consider your move rational or irrational? As an agent, we still consider that rational because these agents decided based on perceptions from input. This is not something like having, bird eyes of the problem or seeing a very, very huge picture of the environment. For example, if we have an autonomous car with mistakes, we had this incident. I think it was one of Google Drive. I don't know which autonomous car. I don't remember exactly. Driver was watching Harry Potter. Put it on autonomous drive. It was Tesla, yeah, Maria. Autonomous drive, and a truck was, crossing the road, and it was painted blue. And somehow, the camera, the AI system mistook the truck with the continuation of the sky, and just crashed to the truck, and unfortunately driver died. Because so was the can we blame a glare of sun, or just was image problem? You're right. Based on perceptions, if you want to blame the agent, well, based on the image and inputs and perceptions given to the agent made a rational decision, right? You expect your agent to get you to the destination within a certain time based on this input image, based on this LiDAR or whatever inputs, and it did it. Okay, so the answer is depends on what you give and what you expect from the agent. This example shows that rationality is not the same as perfection. Rationality maximizes the expected performance. What do you expect it from it? What do you define as the performance? While perfection, perfection maximizes the actual performance, probably with all exceptional cases as well. Retreating from a requirement of the perception is not just a question of being fair to agents. The point is, if we expect an agent to do what turns out to be the best action after the fact, it will be impossible to design an agent to fulfill these specifications unless we improve the performance of the crystal ball and time machine. Impossible things, right? If you expect your agent, your AI to be perfect, you have to give it perfect information. You have to give a crystal ball, to see everything. Or give it the power to do analysis, to do the calculation for everything. The best sensor, if your sensor cannot detect something, even the best rational agent can't do, even human can't do mistakes, right? So we have to be careful on our definitions, our inputs, our outputs, and how we measure the behavior of the agent. Trying to just a model, trying to understand the agent behavior. That's what we are trying to do right now. Our definition of rationality doesn't require any science. Then, because the rational choice depends only on percept sequence to date. If something is not in the perception of the robot, hasn't detected anything, then we cannot blame the AI or agent for that. Rationality is distinct from the omniscience. As I said, all knowing within infinite knowledge. Oh, God of the knowledge. Agents can perform actions in order to modify future percepts. Okay, future percepts, and that's obvious. A driver, when driver decides to turn the wheel, perception will change. So the future perception will change. As to obtain useful information, information gathering, and exploration. These are also keywords. An agent is autonomous if its behavior is determined by its own percepts and experiences, not from outside. So when I call autonomous means it relies on its own perception and experiences, previews, decision, and results. With ability to learn and adapt means first time it takes an action, gets some reaction from environment, and based on that reaction it learns how to behave next time, or it adapt itself in future without depending solely to built-in knowledge. So it also perceives or builds up a knowledge about environment, about the action reaction with environment. Doing actions in order to modify future percepts, sometimes called information gathering. It is important part of rationality. Our definition requires a rational agent not only to gather information but also to learn as much as possible from what it perceives. There are extreme, the agent's initial configuration could reflect some prior knowledge before it goes to the environment and then gains experience. With this experience, it might have the capability to build up the knowledge. There are extreme cases in which the environment is completely known to theory, so a priori, before. So if your environment is completely known, for example, in our vacuum cleaner, so it doesn't need to build up information about environment. Example, consider the dung beetle. So this is beautiful. Unfortunately, I couldn't find any video for this, but this is interesting. This insect behaves similar to an agent. Rational agent is, what does it do? It collects food and takes that food, actually while rolling it to its nest where eggs are. Okay, so this is quite rational and very, very sort of intelligent agent. Okay, but there are kind of bugs in the program of this bug. Okay, there are bugs in the program of this bug. If the ball of the log is removed from its grass and root, the beetle continues its action and pantomime, actually. It just pretends that it's taking something, but there is nothing. But since the program is sort of nothing happened, so I'm still pushing the ball just to the nest. It continues doing that without having anything. So evolution has built an assumption into the beetle's behavior, and when it's violated, unsuccessful behavior results. So you don't see any change. The other example, which I found a video for, and please, I suggest you to watch that video as well. It's very interesting. It's a kind of wasp, so hunter rat. It kills another insect and brings it to its nest for the similar reason. Puts it in the nest for eggs to when they hatch, they can eat the not died but paralyzed insect, and have enough food for the initial. Well, if you look at the video, I can share that with you. I hope it might be. All right, you cannot. But if you watch the video, you see, I suggest to watch this video definitely. If you take the food away, you know, the routine is it brings it close to the nest, goes inside the nest, checks if everything is okay, eggs are there, comes out and drags the insects, the paralyzed insect, or that insect into the hole, right? What happens? It goes and leaves the body close to the hole's door, goes inside, comes back, and takes it in. If meanwhile, when it goes in, you move it somewhere slightly far, not close again, but you move it away, not too far, it comes out, search, finds it, brings it back to the door of the hole again, leaves it there, goes inside to check again. It checked it just a few seconds ago, but it in and comes out to drag it in. But if you repeat this, it will repeat that over and over. It doesn't realize that something is wrong. It's kind of loop. You're trapped in. It just continuously does that over and over. This is an agent. This is a rational agent, but there is a bug. There is a kind of unconsidered situation in the program of that specific agent. Did anyone open the video? No? Okay, I suggest you do it. All right, so have a look at that. That's very beautiful. How kind of what kind of bugs might be there, even in well-developed natural agents. Okay. To the extent that an agent relies on the pure knowledge of the designers rather than its own percepts, we say that the agent lacks autonomy. So if your agent relies on more pure information, means that it's less autonomous. The rational agent should be autonomous, that it can compensate partial or incorrect pure knowledge. As a practical matter, one seldom requires the complete autonomy from the start. Then we have to, when the agent has had little or no experience, it would have acted randomly, unless the designer gives some assistance. That's a general solution. So if I design a robot or to cleaning, so if robot doesn't find any dirt close by, it should start check randomly as one of the solutions. After sufficient experience, then it can start work independently without any help from outside. Incorporation of learning allows the design a single rational agent that will succeed in a variety of environments. All right, environment. Let's see what we have. The task environment, which is essentially the problem to which rational agent is the solution, right? To understand that, to talk about these different agents, we have to understand these basic things, okay? Well, before we design intelligent agent, we need to specify this task environment, and we call that piece, right? So this performance measure, environment, actuators, and sensors. For example, in a taxi driver, what is the performance of a taxi driver? How do you measure performance of an AI taxi driver? So performance are things like how safe, how fast, how legal, how many tickets it gets, how comfortable, how maximize profit. These are measures, right? Things we can think of an AI taxi driver. What is the environment? Environment are roads, other traffic, pedestrians, customers, probably police, and rules. Actuators are steering wheel, accelerator, brake, signal, horn. This things by which it interacts with the environment. Sensors can be cameras, sonars, lidars, speed meter, GPS, odometer, engine sensors, keyboard like a driver, actual driver. So these are PEAS parameters of an taxi, AI taxi driver. Anything you think you should we should add here? Nothing. Another example, medical diagnosis system. If I have a medical system to diagnose, how do you measure that? By healthy patient, minimize the cost, lawsuits, difficulties you get in. Environment are patients, hospital, and other staff, nurses, doctors, people who are working. Actuators, screen display, it tells or answers the questions and tells the results, shows the images and diagnosis, and interacts with the patient or with the doctor. And sensors are things like keyboard. You enter symptoms, you enter findings, you enter patient information and answers, and it can give the advice based on that. So if I'm going to design an AI system to help doctors or patients, this would be a basic PEAS parameters. For part picking robots in industry, in manufacturing, the performance will be percentage of the parts in the correct bins, or percentage of parts in incorrect bins. You also can define both, or you also can add speed. You also can add how much energy, and like any other worker. Also for environment, it will be conveyor belt, parts, bins, and probably other robots working close, or human working close to this robot. Actuators, joints, arm, hand, gripper, and other might have other components as well. Wants to turn on a light, turn off a light, wants to have an audio input or not, different inputs. Sensors are camera, joint angle, other limit switch, RFIDs, other also might be considered as input sensors. Refinery control, similar thing. You define performance, you need to define your environment, you need to define your actuators, you need to define your sensors. This would be the first step to design an AI agent for any application. For any application, you have to make it clear what is the environment and what is the performance, what is the actuators, and what are the sensors of your robot. This is sort of general approach to any sort of agent. Another example, English tutor, again, same thing, students, class, others, and also keyboard and display. We have a table in the book and also included here, talking more about those. Environment types, different environments are possible. So if I do categorize what's going on around my agent, I can talk about what sort of environments are possible, or what kind of characteristics my environment might have. The range of task environments are possible for AI applications. These are, things like characteristics and behavior and type of the environment around us. Okay, things like definition, like environment can be fully observable or partially observable. Means I'll explain that more. Having an environment which our agent can perceive fully or not. Deterministic or stochastic. It can be episodic or sequential. It can be static or dynamic. It can be discrete or continuous. It can be single agent or multi-agent. Okay, multi-agent. I'll talk about them one by one. We say one environment is effectively fully observable if the sensors of the agent detect all aspects of that are relevant to the choice of action. Relevance, in turn, depends on the performance measure. So we call an environment observable when I have, well, my agent sensor can get all relevant information from an environment. Fully observable environments are convenient because the agent doesn't need to maintain an internal state to keep track of the world. What does it mean, internal state? Think about that. If you are in an environment, yourself as a person, you're walking around. Environment is fully observable. You can see where you are, right? You can see your location clearly. You don't need to remember where were you and how did you get here. But if your environment is like a maze, it's partial observable. You can see part of it. You don't see everything. Your sensors can't reach every detail of the environment. In that case, you need to create an internal state. Where were I? How did I get here? And what is the connection? You try to build a model in your brain to connect different things together about environment. This is a simple task. You try to find your path through a maze. Now, if you talk about more complex environment that there are different parameters, different performance items involved, then you need to keep track of everything. How did you get here? How these parameters change? So we call that internal state. An environment might be partially observable because of noisy and inaccurate sensors, or because part of the state are simply missing from the sensor data. Like a driver, which can, suddenly because of snow, because of the fog, because of some problem, loses the part of eye contact. So this driver needs to keep state of the road in their mind because to try to figure out if you're familiar, if you have been in that road, you have to retrieve those information that I know that there is a bend here or there is something here I should be prepared for, or no, you haven't been there before. You have to build up that information based on your observation. If the agent has no sensors at all, the environment is unobservable. So like, blindly moving, you have nothing to build up your information about the environment. One might think that in such a case, unobservable agents to be hopeless, which is not true. But agents, if we be able to define proper goals and a proper agent, they still might have level of success even without any information from environment. Any questions so far? Okay. So, single agent versus multi-agent. The question is how another entity in the environment may be viewed as an agent. So, for example, a taxi driver, who is it a single agent or multi-agent? Or vacuum cleaner, definition. The key distinction is between whether another entity's behavior is best described as maximizing performance measure whose value depends on the agent behavior. So if I have other agents or other items or entities in my environment, if my performance and their performance cannot affect each other, so you can consider that as part of environment. You say my environment has something changing, okay? It's not another agent. But if this agent, performance measure of one affects the other, you can say it's another agent. For example, in chess, the opponent is not environment, it's an agent. Because if I win, he or she will lose, or it will lose if it's a computer. So, and vice versa. If they win, that means I lost, okay? So it would be agent. In a taxi-driven example, avoiding collision maximizes the performance measure of the agent. So it is a partially cooperative multi-agent, because we don't have a taxi driver not necessarily have competition with others, okay? It's better for me and for them both try to avoid collisions, to have things. So they are partially cooperative multi-agent. Some agents in multi-agent environment might also communicate with each other, might not. And remember that in some competitive environments, randomized behavior is is rational because it avoids pitfalls of predictability. If sometimes if you have competitive specifically agents, sometimes randomized movement makes it more difficult for the other side to predict that what you're gonna do to make a strategy plan to win the game. Environment types again, deterministic versus stochastic. If the next state of the environment is completely determined by the current state and action, then the action executed by agent, we say the environment is deterministic. So definition of deterministic is if the next step is completely determined by actions, current state and actions we do, all right? We call this deterministic. A multi-agent environment can be deterministic even though each agent may be able to predict the action of the others. The environment is partially observable, however, then it could appear to be stochastic. So in a multi-agent, if you are playing online with several other people, although environment is deterministic and other agents are playing, but since it might be partially observable, it might look like stochastic environment. Most real situations are so complex that it's impossible to keep track of the unobserved aspects for partial proposed, and they must be treated as stochastic. Also, we say an environment is uncertain if it is not fully observable or not deterministic. The word stochastic generally implies that uncertainty about the outcomes is quantified in terms of probabilities. You have to have a stochastic or probabilistic model. A non-deterministic environment is one in which actions are characterized by their possible outcome, but no probabilities are attached to them. Okay. Non-deterministic environment descriptions are usually associated with performance measures that require the agent to succeed for all possible outcomes of its actions. Episodic versus sequential. In an episodic environment, the agent's experience is divided into atomic episodes. In each episode, the agent receives a percept and then performs a single action, where the next episode doesn't depend on the actions taken in previous episodes. So every time you decide based on what's happening right now. For example, an agent that has to spot defective parts and an assembly line, okay, bases each decision on the current part, regardless of previous decision. Moreover, the current decision doesn't affect whether the next part is defective or not. So this is a good example. You have these parts are coming. Well, you might be able to make it more intelligent trying to predict what's gonna happen next, but it checks each part individually, each part independently from what you had before. Okay, but in sequential environment, the current decision could affect all future decisions. For example, chess and taxi driver agents are both sequential type of, they both work in sequential type of environment. Episodic environments are much simpler than sequential environment. In episodic, you make decision based on what you have right now, and that's it. But in sequential, what you're making now might affect your next 10 moves, your next 20 moves in future. Environment type again, static versus dynamic. If the environment can change while an agent is moving or deliberating, then we say the environment is dynamic for that agent. Otherwise, it's static. So if environment itself changes, it would be dynamic. Static environments are easy to deal with because the agent doesn't need to keep looking at the word while it's deciding on an action, or nor need to worry about the passage of time. So by time, environment is fixed. Dynamic environment are continuously asking the agent that it wants to what it wants to do. If it hasn't decided yet, then comes to deciding to do nothing. So environment itself has a dynamic change, regardless to agent moves or not. So every time agent moves, it might make a change in the environment. That's still, it doesn't make it dynamic. But even without agents move, if environment starts changing, that means it's dynamic. If the environment itself doesn't change with the passage of time, but the agent's performance score does, then they will be semi-dynamic, just under the effect of the agent. Environment type, again, discrete versus continuous. In discrete environment, states are distinct from each other. So you have specific distinct steps in your environment. For example, the chess environment has a finite number of distinct states. Okay, so one move to the other move, they're discrete from each other. But in taxi driving agent, for example, environment is continuous. Things change continuously. You don't have, steps in time. You don't have distinct steps in time. Unknown versus unknown. The environment which our agent already has information about or doesn't have information about it. So the distinction between known and unknown environment is not the same as between the fully and partially observable. These are different. It is quite possible for a known environment to be partially observable. For example, in the game, in the Solari card game, in card games, your environment is completely known. You know how many cards you have, shape of the cards, numbers on the cards, colors of the cards, everything. But you don't know what's going on right now, right? These are different. So I know the rule, but I'm still unable to see the card. So it's not observable, but it's known. In some cases, environment is unknown. It's something even probably more difficult to conceive, to deal with. It's not only observable, but it's also unknown. You don't know relationships in the game. So example is considered. Unknown environment can be in a new video game. Let's say someone puts you in front of a new video game. The screen may show entire game states. You see everything, but you don't know what is that game. You have no idea. You don't have understanding of relationship thing between things in the environment. You don't understand it, so it's unknown. And these are examples. I want you to go through this yourself and make sure that you understand how does it. So these are examples from book again. So tasks. First column gives me the task. For example, crossword puzzle, chess, poker, backgammon, taxi driving, medical diagnosis, and it says whether the environment is observable, deterministic, non-deterministic, episodic, static, discrete, and what type of, how many agents, a multi-agent or single agent. I'll look at a couple of them. Say, crossword is fully observable. You can see everything. There is no hidden information. It's quite deterministic. There is nothing stochastic and changing probabilistically inside. It's sequential. It's not episodic. Time is continuous. It's not based on step-by-steps. The environment is static. It's not changing. Discrete or continuous, it's discrete. Discrete, right? You have time steps, but it's, well, it might be confusing between episodic and continuous discrete. So in episodic and sequential, sequential means your decision will affect your future decisions as well. In crossword, it is. When I choose one, a set of letters, I will restrict my next decision to those set of letters, okay? Because, well, these crosswords are connected to each other. But it's the discrete and continuous is discrete. You find word by word or letter by letter instead, and it's single agent. You are not playing against anyone else. Another example is I don't know, this taxi driving. Environment is partially observable. You don't know everything. It's stochastic, things changing based on probability. It's sequential. Your decision will affect your future decisions. It's dynamic. Your environment, even without you, continues changing. And discrete or continuous, it's continuous. It's not just time steps. It's continuously changing, and it's multi-agent. There are others involved in that. Please check this. These are examples, and if there is any confusion, please come back and tell, we can talk about it and make sure that it's clear. All right. Now, I want to talk about agents type. We talked about environment types. Let's have a short break here, and when we come back, I talk about agent types. It's becoming more interesting. Now, what we did so far, we should have a better understanding of environments. If you are designing an agent for your project or somewhere, now, when you look at the environment, you should be able to say whether this environment is discrete, observable, partially observable, stochastic, dynamic, static, all those details. Any questions so far? Okay, so we'll be back in 10 minutes. Thank you. I want to give yourself and myself a break. So we... Okay. Stop.